Hello there. We are in week 9. Last lecture I did mutation testing for integration, specifically focusing on design integration. So this was the status of our lectures. We are inside mutation testing. The ones marked in green are done. The ones striked out we're not going to do. This we will be doing in the next 2 lectures. We are currently here in applying mutation testing for testing program with focus on integration. In the first part of this, which I taught in the last lecture, I introduced you to generic mutation operators, which talked about changing a calling method in more than one ways, change a call method in more than one ways. We discussed these 5 different generic mutation operators that could be done for integration testing for almost every programming language that supports procedure calls or method calls. Later on in the last lecture, after doing this, what I told you was, we said we will focus on object-oriented integration testing because object-oriented languages have picked up a lot of web applications, enterprise applications are written in object-oriented programming languages. So we said we'll focus specifically on mutation operators that are available for object-oriented programming languages, especially Java. So with that, towards recapping what we need to understand mutation, we recapped the essential object-oriented features in the end of last lecture. So I helped you to recap encapsulation, class inheritance, overriding methods, variable hiding, constructors, polymorphism, and overloading. So we did this last time, so I'll skip through these slides. We'll directly move into looking at Java and what are the specific mutation operators that are available for focusing and doing integration testing for a language like Java. So to do that, one last concept that I would like to specifically recap related to Java is the notion of instance variables and class variables. So instance and class variables both are variables that are associated with a class in Java. What is the difference? We'll see the difference. Class variables are also called static variables. They're declared using the word static. They are static in the sense that there's only one copy of the variable that is shared with all the instances of the class. Instance variables, on the other hand, they belong to an object or an instance of a class, and every instance of the class has its own copy of the variable. Changes made to an instance variable don't reflect. Suppose you have one copy of instance variable in one object, you make a change, it doesn't reflect in all the other copies of instance variable. Like we had access levels for encapsulation, instant variables, where are they declared? They are declared at class level. Class variables are declared with the keyword static, as I told you. And in addition to these two, we also have local variables which are declared within methods in a class. Now what we are going to see, mutation operators for doing integration testing specific to object-oriented features. Without loss of generality, you can assume that we will be focusing on mutation operators for Java, but equally well applies to any other object-oriented programming that shares the same kind of object-oriented features for integrating different pieces of code into one large code. So the following are the generic features that we will be seeing. We will instantiate them with reference to Java, but let's say you use C++ and then it has this feature, you could as well use these mutation operators to be able to do integration testing for C++. So we'll see information hiding related features. We'll see inheritance related mutation operators. We'll see mutation operators related to polymorphism, dynamic binding, method overloading, and classes. So in the slides that follow, I'll be listing about 20 different mutation operators. All of them are meant for testing integration of object-oriented programs. So for each of these operators, I'll tell you what it does, and then wherever applicable, I'll also give you one instance of what is the kind of error that it could be useful to detect while doing design integration. Obviously, when you test your program for design integration, you're not going to be able to use all of these operators. This is meant to be used as an exhaustive list. What we are going to use is a select set as and when we need based on what our focus for integration testing is. So the first operator that I'm going to tell you is called access modifier change, abbreviated as AMC. Don't worry too much about remembering these abbreviations. I just carry them forward because it's useful to list them as you're going on. We really don't need to remember them for any reason at all. What does this operator do? This operator basically changes the access levels. What are the access levels that it changes? It changes the access levels for each instance variable and method. What do we achieve by this? We achieve and get tests that ensure that accessibility is correctly done during integration. The access modifier change operator creates mutants that can be killed only if the new access level denies access to other classes, or it's the opposite. It allows access to other classes, which causes some kind of conflict in name. That's when you can observe a change in the behavior, and then you say applying this mutation operator killed the mutant. So the next mutation operator, in fact all the mutation operators that we will be seeing will only do 3 kinds or 4 kinds of changes. They'll delete something, they will remove something, they will insert something, they will modify something. So the first one that we saw was a modification. The next one that we are going to see is deletion. What does this delete? This deletes what are called overriding or hiding variables. The operator is called hiding variable deletion. By just reading the name, you should be able to figure out what it's supposed to do. It can't be too difficult. What does this mutation operator do? By hiding, by deleting the overriding or hiding variable, we cause references to that variable to access the variable defined in a parent or in any ancestor. This could be a common programming mistake that can be caught during integration testing. The next mutation operator that I am going to tell you specific to Java is an insert mutation operator. In the previous one we showed you about deleting, hiding or overriding variables. Here what we are going to do is we add a new declaration. What are we going to do? What will the declaration do? The declaration has got to do with hiding variables. So declaration is added to hide the declaration of each variable declared in an ancestor. What does this mutant do? This mutant basically hides the variables that are declared in the ancestor, and it tests whether the overriding reference variable reference is correct or not. So these mutants can be killed by test cases that show that the reference to the overriding variable is not correct. So the next mutation operator in our long list of mutation operators that we are going to see, what does it do? It's a deletion mutation operator. Instead of working with variables, it works with methods. It's called overriding method deletion, abbreviated as OMD. What does it do? It removes the entire declaration of the overriding method. Please note, we're not removing the method, we're removing the declaration of the method. What will then happen? The references to this method that happen in a class will then use the parent's version, right? So if this happens, then it ensures that the method invocation is indeed to the correct method and not to the wrong one. By deleting, if there is a problem, you will be able to find out because the method itself is deleted. So if there was a correct reference, there will be an issue. You will be able to kill the mutant and observe an error. But if there was an incorrect method, by deleting this method reference, deleting the method declaration, you will not be able to observe a change. So that means you will not be able to kill a mutant. The fact that you can't kill a mutant reveals an error in this case. The next operator is called overriding method moving, abbreviated as OMM. What does it do? Each call to an overridden method is moved to the first and to the last statements of the method, and wherever it is in the program, it is moved up by one statement, it's moved down by one statement. In the previous one, we deleted the declaration of the method. Here we're not deleting it. Instead, there is a particular line in which the method is declared. What we do, the declaration or the call, we move its location within the program source code. We move it to the first statement, we move it to be the last statement, we move it one statement up, we move it one statement down. What will this test? This will test the following. Typically, overriding methods in child classes, they often call the original method in the parent class for some reason. For example, they could call it to modify a variable that is private to the parent. There could be other reasons also. One common mistake is to make the call to the parent's version at the wrong time. You called it too early. Maybe by the time you called it, it was too late to use the variable. So moving around the call, the statement of the call, we'll be able to correctly detect whether it was called at the right time. So killing such a mutant will detect errors related to where the call is made. If it's made at an inappropriate place, it will be obviously detected. So the next operator also deals with overridden methods. So I'll go back. We deleted overriding methods. We moved overriding methods. Now we are going to rename overriding methods. Overridden method rename, abbreviated as OMR. What does this do? It renames the parents' versions of the methods that are overridden in a subclass so that overriding does not affect the parents' method. What is this operator designed to check for? This mutation operator basically checks if an overridden method actually causes problems with other methods. So here is an illustrative example. Let's say there are two classes called list and stack. List is the parent class. List has a child class called stack. Maybe list is a list operations and stack is one of the ways of implementing a list, whatever it is. So there are two classes, list parent class and its child class called stack. And there are two methods, a method called M, a method called F. Both of them are present in the class list. And in the class list, method M calls the method F. In addition, method M and F are also present in the class stack. How are they present in the class stack? M is inherited without a change in the class stack, but F is overridden in the class stack. So now when I rename one of them, what will happen? When M is called on an object of, let's say, type stack, it calls the stack's version of F instead of the list's version. This kind of problems I can detect by using this mutation operator. I hope this is clear. Moving on, the next mutation operator we are going to see relates to this keyword called super. If you remember, we used super. Why did we use it? We used it to refer to appropriate variables in an ancestor, right? In an ancestor class. That's the context in which I had introduced this when I told you about object-oriented features in the last lecture. So super keyword deletion, what does it do? It just simply deletes the super keyword, which means what? After deletion, the reference will be to the local version of the variable instead of the ancestor's version. So let's say if you had super.x, you delete the word super and directly refer to x. So the x that I am referring to now is in the local version and not in the ancestor's version. So what kind of errors can this reveal? This can reveal errors that ensure that hiding or hidden variables or overriding or overridden methods of variables are used appropriately. So if it was meant to be actually from the ancestors class, not the local version, then deleting it will use the local version and reveal a potential error. So the next mutation operator is called parent constructor deletion. So it deals with constructor. So each call to the super constructor is deleted as the mutation operator describes. What happens in this case? In this case, after deletion, the parents or the ancestors default constructor would be used. Now, to kill such mutants which delete the super constructor operator, what do we need to do? We need to find a test case for which the parent's default constructor creates an initial state that is incorrect, because that's when I will be able to observe an error about using the parents or an ancestor's constructor. Otherwise, I will not be able to observe any error. So the next mutation operator changes types. Whose type that is changed? It changes the actual type of a new object. Where does it change? It uses this new statement that's available in Java to be able to change the type of the new object. What kind of problem this causes? If you do this, then it will cause the object reference to refer to an object of type that is different from the original actual type. Is that clear? Because I have changed it now in the new statement. So now what will happen? The new actual type that it's acquiring must be the same type family of the original actual type. I need to ensure this because you remember the good old thing about mutation. After mutating a program, the program must compile. It should not be syntactically illegal. So type change, if you do, then the type change better be consistent so that the mutation can be applied through a ground string to get a new program that can still compile. And then we can worry about whether we can strongly kill it or weakly kill it and so on. So the next operator in our long list is what is called declared or parameter type change. This one slide actually contains two mutation operators. Both the mutation operators are about changing a type. One changes the type of a declared type, one changes the type of a parameter. So the declared type of each new object or each parameter object type is changed in the declaration. So what will happen? The new declared type must be an ancestor of the original type and the instantiation will still be valid because that's how we do it. To kill such mutants where the declared type of an object or the parameter is changed, what should a test case do? It must cause the behavior of an object to be incorrect with reference to the new change that I have made to the type. So if that happens, then I know that there is a problem with my original declaration, or maybe my original declaration was fine. So that's the integration feature that I test. So the next one that we are going to see is also a type change, but this is a type change called reference type change. What does this do? Here the reference is changed, which means the right side objects of assignment statements are changed to refer to objects of a compatible type. The right hand side of the assignment statement or the reference statement, the type of that is changed. Not the entire reference, but only its type. For example, if an integer is assigned to a reference of type object, then you could make a type change and change it to that of a string. In general, it may not be allowed. Integer changing to string, there will be big problems related to compiling. But here, it will work fine because both have descended from object, so both can be assigned interchangeably. And this will again detect any errors that relates to changing of types and the types of references. Moving on, the next operator that we are going to deal with is related to overloading methods. In fact, we will work with overloading method change here, overloading method deletion here, two operators. So what does overloading method change do? For each pair of methods that have the same name, the bodies are interchanged, which means the code that corresponds to these methods, the entire code that corresponds to these methods, they are swapped. They are interchanged. Then what is this will test? What sort of error this will test? This will test any error that relates to overloading methods being invoked properly. If they are not invoked correctly at the same time, then one is invoked instead of the other, you will be able to kill the mutant and detect any errors related to proper invocation of overloaded methods. So next operator also deals with overloading methods. Instead of changing them, it deletes them. So the operator is called overloading method deletion, abbreviated as OMD. What does this one do? Each overloaded method declaration is deleted. Please remember, there is no point. Suppose I have more than one overloaded methods. In one shot, I cannot apply this mutation operator and delete more than one. That will violate the problem of applying one mutation operator at a time to be able to mutate a ground string. This mutation operator can be applied to delete any overloaded method declaration, but not more than one. That if you apply it to more than one deletion, then it will mean that you're deleting more than one at a time. That's not allowed. So you delete each overloaded method declaration one at a time. Choose which one to delete based on what you want to focus and test. What will this operator ensure? This operator will ensure coverage of overloaded methods. Why? Because I delete, then what will happen without it? Then I test that. Then I put this one that I deleted back and delete something else. Then I test what happens without the second one that I deleted, right? So all the methods must be invoked once as and when they take turns to get deleted. If a mutant still works correctly without the deleted method, then it could be an error. It could be an error in invoking one of the overloading methods while doing integration. The incorrect method may be invoked or an incorrect parameter type conversion has happened. If nothing happens after deleting one particular method, then maybe it was a piece of dead code and you could do without it. Right? So if you get an equivalent mutant, then it means that the method was dead code and you could do without it. Otherwise, you will definitely be able to kill the mutant and observe one of these kind of errors. So the next operator we will see changes the order in which arguments are passed during method invocation. It's called argument order change, abbreviated as AOC. What does this do? The order of the arguments in a method invocation is changed to be the same as that of another overloading method if it exists. This causes a different method to be called because I'm changing the arguments, and hence it checks for common fault in the use of overloading. What happens because something could be called out of order, I've changed completely. So then if there is an error because of the use of overloading, I will be able to catch it. So So the next mutation operator also deals with arguments, but here we did change the order of arguments. Here we changed the number of arguments. Let's say you had 3, you could make that 2, you could make that 4. That's what we mean. Change the number of arguments. So number of arguments in method invocations is changed to be the same as that of another overloading method, provided there is one such method that exists and you could replace it with that. What will this help? This will help to check that the programmer indeed invoked the correct method. He didn't pick up the wrong method to invoke. And when new values have to be added, they are constant default values of primitive types, or they are the result of default of constructors for object. Is that clear? So moving on, the next operator that we are going to see, we still have a long way to go. Remember I told you 20 operators. So we're probably around 15. So we still have a good number of operators to go. So the next operator that we are going to see deletes this keyword called this. You remember Java has this keyword called this. What does the keyword this do? Within a method body, when I use a keyword this, it refers to the current object of the member variable is hidden by a local variable or a method parameter that has the same name. Now if I delete it, then what will happen? It checks basically when I apply this mutation, the resulting program, if I'm able to kill it, then I'm basically checking if the member variables are used correctly by replacing every occurrence of this dot x with x. So here, unlike the earlier one, when I said this keyword deletion, you have to be careful. You have to delete more than one keyword of this, because if you keep one and retain one, there could be problems. So sometimes you might have to delete one if there's one, but if there's more than one related one, you have to delete all of them. Then the next mutation operator is called static modifier change, abbreviated as SMC. What happens here? Remember static variables, I told you right in the beginning, instance variables and class variables of Java. Class variables are static variables. So each instance of a static modifier is removed, and the static modifier is instead added to the instance variables. What will happen? This basically checks if the various instance variables and class variables that have been declared around a piece of code are declared correctly and are being used at the appropriate place. So the next one, variable initialization deletion, VID. What does it do? It removes initializations of each member variable of a method or a class. They are not initialized at all. If they are not initialized, what are the kind of errors that you could detect? Please remember, instance variables can be initialized in the variable declaration or in the constructors for the class. So when I remove variables, this operator removes the initialization so that member variables are initialized to default values, and it basically checks if the program will still run fine with reference to the initializations at the default values. So the last one in our really long list of mutation operators, what does it do? It's called default constructor deletion, DCD. It deletes each declaration of the default constructor with no parameters. What can this ensure? This ensures that the user-defined default constructors are implemented properly. Suppose I delete, and after deletion the program still works fine, which means it's an equivalent mutant, then clearly I may not need it, right? There's something wrong with my implementation. Suppose I delete, and after deletion my program does have a problem, then I have implemented it correctly, at least at the integration level. So what did we do? We provided an exhaustive list. It must be tiring, it must be a little confusing in fact to go through such a big list. You might want to play this video once again to get the list right. But intuitively what it tells you, the list that we provided of 20 different mutation operators, it basically focuses on entities related to integrating methods, classes inheriting from each other, overloading, overriding, their access levels, and it makes changes to all the places that focus on putting these together and tells you an exhaustive way of mutating to test this integration. Obviously, when you have a piece of code that you want to test for design integration, you're not going to be able to consider all of these operators, not even half of them. Carefully, based on the integration feature that you want to test, you will pick up one or two of these operators, maybe a few more, and apply them to see the feature that you are going to test. So the choice of the operator is based on the feature that you want to test, and that is completely to be decided by you. The focus of this lecture was to be able to provide an exhaustive listing to help you choose from this varied variety of choices that are available. So I hope this exhaustive listing of mutation operators for object-oriented integration testing helps you. You could use it when you're integrating Java programs or C++ programs where all these features are available. In the next lecture, we'll move on to using mutation testing for specifications, input grammars, and XML models of inputs. Thank you.